Now we'll say our dielectric interface. This we will call region number 1. This region we called region number 2. The radius of region number 1 we stated was B. And then we had our shield. And that radius was equal to D. We showed that the potential in region number 1, which is R, is greater than A and less than B, this is a function of radius, was equal to the negative of the potential of our source times the quantity one over the permittivity of region number 1 times the natural log of R over A divided by our symbolic term, which we identified as a constant and called it D, or I'm going to call it script D, so we don't confuse it with the electric flux density, minus 1. In the same fashion, the potential in region number 2, this was equal to, that's valid for R, greater than B and less than D, that this was equal to minus V naught times the quantity 1 over the permittivity epsilon 2 times the natural log of R over D, and that's divided by script D, where script D is equal to 1 over the permittivity epsilon 2 times the natural log of D over B plus 1 over the permittivity epsilon 1 times the natural log of B over A. So that represented the potential, the equivalent magnetic field for region 1, and I'll put this down over here, region 2. That the electric field in region 1 is in the radial direction. It's a function of radius. We'll call that E sub R1, and that's equal to the potential V naught, so it'll be the potential of our source, divided by the permittivity epsilon 1 times R times script D. And in region number 2, the electric field E sub R2, function of radius R, is equal to the potential V naught over the permittivity epsilon 2 times R script D term. So this is where we ended last time we met. Our task now is to determine the capacitance, the total capacitance. Let's write down the definition for the total capacitance. This is going to be equal to the total charge on one of our bodies, the most positive body, divided by the potential difference between the two bodies. And the potential difference between the two bodies is already known, and it's fixed, and that's equal to V naught. So we'll say, but V is equal to V naught. Our task now is to determine what Q is. Well, we used we talked about two other boundary conditions that we didn't use in the development of our unique equation for the voltage and potential inside our system. And those two boundary conditions are actually the ones that are going to be useful in this case. One of our boundary conditions tells us how the field, just external from the boundary, is related to the surface charge. So consequently, let's look at that particular case, in particular for the inner conductor. So I'm going to redraw the inner conductor. It is of radius A. And let's build a pillbox. And draw out our differential surface elements, pointing normal to the surface, away from the volume enclosed. Let us identify what is considered to be positive. Positive is radial. So that's considered to be positive. And we observe that the pillbox, the upper portion of our pillbox is in region number 1, and the lower portion is in the conductor. Consequently, let us write down Gauss's law. Gauss's law states that if we evaluate the electric flux density around the closed surface S bounding a volume V, that this is going to be equal to the charge enclosed, which in turn is equal to evaluating the surface charge density over the surface S, which is going to be sandwiched in the element of surface in region 1 and the element of surface in the conducting region. Since the field inside a conductor is equal to 0 by the nearly free electron model, we don't have to solve for D in that particular case. We can force it to be 0. In region number 1, we see that the direction that we said is positive is in the same direction as D sub S, and therefore its dot product is 1, and it's positive. Hence, we have the electric flux density in region number 1, and this is the normal component, and that normal component is in the radial direction, same direction as ds is, function of radius. This is going to be equal to, and I'm going to put a plus sign here to show that we did argue the sign out, our surface charge density, which is a function of R is equal to A, because it's only valid at the surface interface between the two mediums. And this one here is going to be R is equal to A as well, but A plus as compared to A minus. So we are in region number 1. Okay. So as long as we know what the electric flux density is, we can determine what the surface charge is. So we know what the electric field is, and we know that the electric field is connected to the electric flux density, and they're connected by the constitutive relation. D is equal to the permittivity of our medium times the electric field. As a result, we can then state that the surface charge at R is equal to A is equal to the electric flux density of region number 1 at R is equal to A plus, which is equal to the permittivity in region number 1 times, since we're in region number 1, we must look at the electric field in that region. And I'll write it out. And then this is evaluated at R is equal to A plus, which is in turn equal to the permittivity epsilon 1 times the potential V naught divided by the permittivity epsilon 1 times R, where R is equal to A, times script D. The permittivities drop out, and consequently, we see that our surface charge density at R is equal to A, should be an A here, not a 0, is equal to V naught over A times D. So that's the surface charge density. If we go back to our recipe, we need the total charge. Consequently, the total charge, Q of T, on the inner conductor is going to be equal to evaluating our surface charge density along the surface of that conductor, that inside conductor. And consequently, writing out the definitions first, we see that ds is going to be equal to r d phi dz in order to cover an area element on that cylindrical surface. Here we see that phi varies from 0 to 2 pi around the cylindrical surface, and z will vary from z to z plus delta z. And we'll talk about what that delta z means shortly. We see that our surface charge density is a constant that can be pulled outside, and wherever we see an r, we must force r to be equal to a in order to be on the right cylinder. Consequently, this is going to be equal to V naught over A times script D. The area, the element of surface is going to be equal to A times 2 pi times delta Z. You see that the factors of A drop out, and hence this is going to be equal to 2 pi times delta Z times V naught over D. Consequently, the total capacitance, and I have enough room to squeeze it in, This is going to be equal to the charges in the numerator, so that'll be 2 pi times delta z times v naught divided by script d. And that in turn is going to be equal to 2 pi times delta z. Oh, don't forget the v naught down here as well. That's the potential difference between the two bodies, times delta z divided by script d. Now, what's up with this delta z? Now, we are not looking at the total capacitance, really. We are going to look at the distributed capacitance. Why? Because if we take the total capacitance, we must take the total area that charge is distributed over. But the area, we stated that our coaxial cable was infinitely long. So the area over the cylindrical surface goes to infinity. And delta z goes to infinity. Therefore, your capacitance goes to infinity. And that's not going to mean much of anything. So consequently, let us look at a small region in capacitance, and let us divide through the capacitance by that element of length that goes to infinity. This is going to give us what we call the distributed capacitance. And hence, that capacitance, by definition, we'll place a bar on top of it, and that's going to be equal to the capacitance in farads divided by delta z. So we are removing the element that goes to infinity. Where would something like this be useful? I'll get to that in just a minute. Let us continue on with this line of thought first. Let us write out what d is, because now our capacitance per unit length is going to be equal to 2 pi. Delta z has been removed, divided by script d. And this is going to be equal to 2 pi over the quantity 1 over the permittivity of region number 2 times the natural log of d over b plus 1 over the permittivity epsilon 1 times the natural log of b over a. Well, engineers like to play games, so we're going to play a game with this. Consider the following. Let us assume that our interface section at B approaches D, or maybe I should say D approaches B. In the limit, when D is equal to B, we observe that the natural log of 1 is equal to 0. Let us define this capacitance per unit length as C1. And that's going to be equal to 2 pi over the permittivity of region number 1 times the natural log of b over a. Now let's take the limit. When b, or I should say a, approaches b. So when a approaches b, we lose the region number 1 altogether. And we see that that's the case here because the natural log of 1 is 0. And hence, the capacitance per unit length in this particular region, we'll call it region number 2, is going to be equal to 2 pi over 1 over the permittivity of region number 2 times the natural log of d over b. Now, if we look at our expressions, we see an interesting effect. We see that if we substitute these guys into here, that my capacitance, my total capacitance per unit length, is going to be equal to 1 over the capacitance per unit length 1 plus 1 over the capacitance per unit length 2. And what is that a sign of in circuit theory?
Parallel circuit?
Oh, capacitors in series act like resistors in parallel. Inductors in series act like resistors in series.
Yep.
So this is a representation of two capacitors in series. If we go back to our original diagram, we can see that this represents a capacitance, and this represents a capacitance.
Oh, in series.
And they are in series. Now this is something I didn't cover in class, and I should have. That's weird. Why is it weird? Well, at the interface B, we don't have a metal plate. So how can it be two capacitors in series? But what we do have at R is equal to B is an equal potential surface. If we have an equal potential surface, we can take a metal plate and form it to fit exactly that particular surface, and our problem has not changed. Why hasn't it changed? Because the electric field lines in region number 1 terminate on that metal surface, that metal cylinder, perpendicular to that cylinder, because it's an equal potential surface. And the electric fields in region number 2 originate from that same equal potential surface, which is just the metal itself. So consequently, the metal, being an equal potential surface, only has to conform to the surface geometry to be equivalent to that particular geometry. And hence we haven't changed the problem at all. Except for there's going to be charge brought to the surface of that metal to terminate and originate the field lines. Terminate the field lines in region number B, or actually there would be terminating and originating the field lines in region number 2. So region number A would be the termination of it. Okay. Before we did two things in this problem. One, we also calculated determined the distribution of charge over the surface. In this particular case, the surface charge density is constant, and hence over the surface of the inner conductor, we see that our surface charge is distributed in this fashion. We should expect that the surface charge at the outer conductor is going to be equal to, in number, the surface charge on the inner conductor, if I count up the number of charges placed over that surface. But we would anticipate that the surface charge density is not the same, because the inner conductor is pretty small in circumference compared to the outer conductor and therefore those numbers of charges of equal number have to distribute over two different areas. Okay, so we solved that particular problem as well in calculating surface charge. One more thing. This distributed charge concept. When will anybody ever use it? Let's take a look at a piece of wire. Suppose that I have a piece of wire and I string it in a straight line. So that represents one wire, and this represents our second wire. And I allow the wire length to become quite large. And I want to look at only a small section of that wire between Z and Z plus delta Z. So I'm going to try to model this wire, and I'm going to model this wire based on some of its properties. We know that the upper wire carries a current, and that current flows in this direction. Therefore, the current in the lower wire flows in the reverse direction. Seems to satisfy circuit theory concepts so far. What if I took a hammer and I pound this wire flat? And I took the same hammer and pounded this wire flat, and I had the two flats looking at each other. What do you see? You see that this particular wire appears to look like a capacitor. We see that this wire has current flow in it. If there's current flow, you learn back in your circuit theory that this is of a sign of inductance. We see that if our dielectric between the two wires is not very good, we have some conductance. Oops. And remember, conductance is the inverse of resistance. And we have current or resistance in the upper wire because the wire is not a perfect element. And I drew that just like an inductor. There. So we now have a circuit model for that wire. Let's redraw that circuit model, and it's only valid between Z and delta Z. So here's our model. We've got this resistor, this inductor. We have a capacitance effect, and I should put that on your screen. We have a conduction effect, and that's just for the first delta Z distance. Let's cascade these guys. And this goes on forever. Let's put our device values in this. Here's a resistance, here's an inductance, this is a capacitance, and this is a conductance, etc. And remember that this position is Z, and this point here over here is Z plus delta Z. Consequently, I'm only looking at the resistance not along the total wire, but only along a small section of that wire. Therefore, that resistance R is going to be equal to R bar times delta Z. R bar is the distributed resistance. C is equal to C bar times delta Z, and so on and so forth. Consequently, we now solve our problem in terms of their distributed parameters as compared to the total resistance, because we're only looking at a small section of our line. One might say, okay, who cares? Well, maybe everybody cares, because notice that the voltage drop at this particular point, V, a function of Z, is definitely different from a circuit's point of view from the voltage drop at this particular point, V at Z plus delta Z. And now you're on the way to solving a transmission line where the wire itself completely violates the simple circuit laws that you developed back in circuits 1 and circuits 2 and used in your electronics class. That implies that the voltage drop between the end of the wires and any intermediate position between the wires is not going to be the same, except for in DC when all transients have died away. This is this cause and effect relationship that Einstein says it takes time for a signal to propagate. And in these geometries, that time can be shown to be equal to the speed of light. Okay, so this proves, at least in a theoretical point of view, the experiment that we developed in our class on the first day. We took an oscilloscope and connected a transmission line to a power supply, a function generator, and placed a voltage at the input of that generator and compared the input voltage to the output voltage along this particular long coaxial cable. And we showed that if the frequency is high enough, that the Lissajous pattern says that the voltage at the input and output are not the same. And consequently, this violates what we taught you back in circuit theory, where causality was not an issue. Okay, let us move on. We worked through one more problem, and we'll work it with you as well. This is my last example problem for electrostatics. Our next lecture is going to be moving into the concept of current. And current is a very difficult parameter to understand, believe it or not. This problem is a solid state problem. It was requested that I solve a solid state problem in this course, at least one, to prepare you for future and upcoming classes. So we are going to assume that we have two semiconducting materials, a P material and an N material. We're not going to go into the details of solid state. We'll leave that for your upcoming classes. But they are two different materials and both have a semiconducting nature associated with it. We will set up a coordinate system. We will choose this direction to be equal to y. We'll choose this direction to be equal to x, and z is coming out of the board or coming out of the sheet of our paper. And this point here is x is equal to 0. We will identify this as being our N material, and it's going to have a permittivity epsilon sub n. The length of our N material we will identify as being x sub n. Our P material is going to be on the other side of the x is equal to 0 plane, and it'll have a permittivity epsilon sub p. The length of that material is going to be equal to x sub p. And the contact electrodes that are attached to the semiconducting medium, we will assume are grounded. If we look at the distribution of the dopant that's placed in these materials, donor electrons, or positive charge, with a distribution that looks something like this, and a charge density, which is equal to Q times N sub D, where D represents donor. That's going to be placed in the N material. In the P material, we're going to place acceptors, and acceptors have a different sign associated with it, and that sign is negative. The density of our acceptors is equal to minus Q times N sub A, where A is for acceptor. Inside our material medium, the donors and the acceptors must rearrange themselves into their lowest energy state, giving rise to charge neutrality. And consequently, for this particular problem, we must force the condition of charge neutrality which is x sub p times n sub a is equal to x sub n times n sub d. So this is a condition that must be satisfied for this particular problem on how the charges redistribute themselves. We will use the symbol rho to represent the volume charge density inside our two mediums. And inside the N material, it's going to be the donors. And inside the P material, these will be the acceptors. And these charges are placed inside the material medium, and consequently these charges are free charges and can move within the semiconducting material. So consequently, because we do have free charge inside the volume, inside the P region and inside the N region, we must make use of Poisson's equation. So let us write down Poisson's equation. The Laplacian acting on the potential inside the region of interest, this must be equal to a negative of our volume charge density of free charge divided by the permittivity of the medium. And the medium is either P or N in nature. And of course, the volume charge density follows suit in terms of acceptors and donors in the particular regions. The question is, at this point, how do we solve the problem? Our potential is a function of function of three variables. And I mentioned to you that I will only give you a one variable, the potential will only be a function of one variable in your problems. Well, we are going to assume that the extent of our medium is infinite as far as y and z is concerned. So we'll put that down over here. Here, y is between minus infinity and plus infinity, and z is between, I'm not quite hitting it here. Do it on the next line. Z is going to be greater than minus infinity and less than infinity. So we can't see the ends. But we do observe that as we walk in the z direction, that we are seeing a lot of different things. Let's point them out so we know what we're supposed to be looking at. We can't argue symmetry in x. Why? Remember, you shrink yourself down, you move a little distance, and you look. Well, you have to ask this question. What is different with respect to bound charges? What is different with respect to free charges? Free charges not only in region N, but also in region P. What's different in the geometry? And what's different in the contact electrodes? And each of these things are going to be seen as different effects as we move closer or further away with respect to X to an interface. And hence, we can't, our potential must be a function of X. Since the P region and the N region are different, we have a discontinuity at the interface, and hence we must solve Poisson's equation in both regions separately. So let's look at the P region first. And we observe that this is going to be the Laplacian operating on the potential V sub P, which is a function of position x. This is going to be equal to the negative of our free volume charge density associated with our acceptors divided by the permittivity epsilon sub A. Writing out the Laplacian, looking at only those terms that are going to survive, since V is independent of Y and Z, we don't need to evaluate the partial differentials with respect to those parameters. We only have the second partial derivative with respect to X to be concerned about. But notice that our potential is only a function of one variable, and therefore the partial derivatives can be replaced by total derivatives. And we're going to write down our total derivative slightly differently. It's really the derivative of the derivative gives rise to a second order derivative operating on our potential V sub P, and that's going to be equal to the negative of rho sub V Fa divided by the permittivity of that medium. That is multiplied through by dx. Well, this will be the differential of the change in our potential with respect to x. And this is equal to the negative of our volume charge density for the acceptors divided by epsilon sub A times dx. Our next step is to integrate. The integral of a perfect differential is the argument of the differential. So that's going to give us the derivative of V sub P with respect to x. On the right-hand side of our equation, this is going to give minus the volume charge density of acceptors divided by the permittivity epsilon sub A times the integral of x times the integral of a constant, which is equal to x. And we come up with a constant of integration. And we'll identify that constant of integration to be equal to A sub P. Now we play the same game again. Multiply through by dx. And integrate. Plus a constant of integration, which we will identify as B sub P. And this is going to give rise to the potential function of x, which is equal to minus our volume charge density divided by 2 times the permittivity epsilon sub A times x squared plus A sub P times x plus B sub P. We have now calculated the potential based on our starting relationship. Well, we observe that the P region and the N, for the P region, we observe that the P region and the N region look very similar. They have a different charge distribution, but the charge density is a constant. It's a different permittivity, but the permittivity is a constant, and the geometry is the same. And as a result, we can use this same expression that we obtained for the P region. Let's define this with our subscript P's. And write it for the X region, as long as the N region, as long as we're careful with sign. So let's do that. We'll say by analogy. Before we do that, because I have room, let us also identify our free volume charge density. So this will be where our free volume charge density of acceptors is going to be equal to, looking at our graph, minus, based on minus negative charge, Q times the number of acceptors per unit volume. In this case, n sub a and n sub d are number densities, and therefore they have units of number per meter cubed. Okay, now let's look at our N region. Well, we do observe a number of different things. First of all, our volume charge density is going to be different. It's going to be based on donors, not acceptors, and those donors are positive charge. So we'll see a sign difference there. We'll see a notation difference. Let's write down our governing equation. So we'll see that notation difference right away. We have the Laplacian operating on the potential in the N material, function of x, and that's going to be equal to our volume charge density due to our donors inside our medium. So that's free volume charge density divided by the permittivity, epsilon n, and consequently this simplifies and is equal to plus our volume charge density for the donors is going to be, it's not going to be plus, is going to be minus the charge Q times the number of donors divided by the permittivity of our N material. Now let's scroll down here a little bit, and we observe that, is this expression right? Here. We stated the signage for our volume charge density. For the acceptors, we see that's going to be negative. For the donors, we see that's going to be positive. Therefore, our volume charge density is going to be flipped in sign, or if you like, whenever we see an N, we replace D by A, or A by D, and we replace P by N, and we will get the same expression. Consequently, let's do that. Going back to this expression here and making that change in notation, we have the potential for our N material, function of x. This is going to be equal to, now the volume charge density is going to change sign relative to the signage used for our acceptor. So that's going to be equal to plus, and let us write out what our volume charge density is for the number of donors. That's going to be equal to Q times the number of donors per unit volume divided by 2 times the permittivity, epsilon sub n, times x squared, plus a sub n, our new constant of integration, times x, plus b sub n. We have a second order differential equation, and therefore we have two constants that must be determined by boundary conditions. Okay, so we should be pretty much set now. And I'm just checking my work to make sure that we're on the same paragraph here. Okay, not quite. Let us substitute this into here and then check our sign. So I'm going to move this out of the way. I'll go back up here and say this is minus infinity for z, and that's going to be less than infinity. And this is going to be equal to, we've got a minus sign here and a minus sign there. It gives us a positive sign. So that'll be our charge Q times the number of acceptors divided by 2 times the permittivity of our P region. So I seem to have not quite followed my schematic diagram. Okay. Times x squared plus a sub p times x plus b sub p. Okay, that looks good. Now we have a change in sign from n sub a to go to n sub d, and that gives us a minus sign. So this one's minus. And now we should be set. Yes. So check this sign out, make sure it's negative. And upon substituting this into here, this minus sign and that minus sign cancel, giving rise to a positive. Okay, we're going to, because I have a new sheet, we're going to rewrite our solution so far and then write down our boundary conditions. Therefore, the potential in the P region, function of x, is going to be equal to the charge Q times the number of acceptors per unit volume divided by 2 times the permittivity epsilon sub p times x squared plus a sub p times x plus b sub p. This is going to be valid for x being greater than minus x sub p and less than 0. Let's look at our n region, the potential in our n region. We argue that this is going to be equal to minus the charge Q times the number of donors per unit volume divided by 2 times the permittivity of our n material times x squared plus a sub p times x plus b sub p. No, that's b sub n. So we have 4 equations and 4 unknowns, and this is valid for x being greater than 0, but less than x sub n. Let's look at boundary conditions. Well, we observe one simple boundary condition, and that is at x is equal to x sub n, the potential in the n material must be equal to the potential of our ground. And our ground is a zero potential. Consequently, one of our boundary conditions is based on the continuity, or the continuity of the potential across the boundary. Hence, this will be at x is equal to x sub n, the potential at x is equal to x sub n minus must be equal to the potential of our n material. Actually, we're in the conductor now, so we'll say that just the conductor at x is equal to x sub n plus, but the conductor is grounded. Since it's grounded, we force it to be equal to 0. Therefore, the potential in our n material at x is equal to x sub n minus, this must be equal to 0. That's one boundary condition. We have a similar boundary condition at x is equal to minus x sub p. And that too is grounded. So consequently, the potential in our p material at x is equal to minus x sub p minus. So we're just inside. This is minus x sub p. We are just inside that region, which is the p region. This must be equal to the potential in the conductor at x is equal to minus x sub p plus. But the potential inside the conductor we choose as our reference is equal to 0. So that gives us two boundary conditions. Let us look at another boundary condition. Well, the only boundary that we have left is the semiconductor boundary. And we know that the potential must be continuous across that boundary. Therefore, at x is equal to 0, we have two boundary conditions. One dealing with the continuity of our potential. Therefore, the potential in the p region at x is equal to 0 minus. This must be equal to the potential in the n region at x is equal to 0 plus. In the same fashion, we have one other boundary condition, and that one is a little bit more difficult to remember, and that deals with Gauss's law. Gauss's law states that if we evaluate the electric flux density around a closed surface bounding a volume V, that this is going to be equal to the charge enclosed, and for our purposes, is going to be equal to the surface charge over the interface, ds, based on its surface charge density. And that would be free surface charge density. So let us draw our diagram. This is region number P. This is our N region. This is our interface at x is equal to 0. Let us draw our pillbox. Let us draw ds. So this will be ds sub n. And this one will be ds sub p. Here we go. And it is a vector. And let us look at our positive direction. Our positive direction in x is in that direction. Therefore, looking at Gauss's law, this is closed surface. Realizing that we are going to lose the cylindrical side of our surface in the limit, we see that the electric flux density in the N region points in the same direction as ds sub n, and therefore its dot product is going to be positive. So we're going to write down this condition in terms of d. So this will be dn. N represents normal. Actually, we have n representing too many things here, so I'm not even going to talk about subscript normal. N represents the N material. So this will be the electric flux density in the x direction in our N material at x is equal to 0 plus. That's going to be equal to the electric flux density of our N material. You know what? I've got to be minus the electric flux density of our N material. Actually, this is P material now because we are at the position x is equal to 0 minus. And notice that d sub s is pointing in the opposite direction of what is positive, and hence the minus sign. And that's going to be equal to, looking back at our law, the free surface charge density at x is equal to 0. Now the question comes in, do we have a free surface charge density on the surface? And the answer is, you've got a free surface charge density throughout the volume V. That's where you place the charge. Yes, charge can go on the surface, but they're not fixed on the surface. And therefore, is kind of a probability thing. And hence, we will force the free surface charge to be equal to 0 and solve for the fields across the boundary. Hence, with that type of argument, this is equal to 0, and we have the electric flux density in the N material being equal to that for the P material. But now let us break it down quickly so we don't have to spend so much time writing a sprout. We know that our electric flux density is related to the permittivity, in this case of the N material, times the electric field in our region, and that's going to be in the x direction. And we know that the electric field can be expressed in terms of the negative of the gradient of our potential in the N material. And this would be the gradient associated with the normal component. Therefore, I have to use N to be normal here. The normal component of our potential V. So consequently, writing D in terms of the potential will give rise to minus the permittivity in the n region times the derivative with respect to x operating on the potential in the n region at x is equal to 0 plus, and that's going to be equal to, this sign goes from a negative to a positive when I bring it to the other side, but because the gradient is also related to in a negative way, I must retain the minus sign, times the permittivity times the change of the potential of our P material at x is equal to 0 minus, looking at variations with respect to x. This is our fourth boundary condition. So I'm going to box each of the boundary conditions, and our next step is to apply the boundary condition. So let's look at region at x is equal to n, x is equal to x sub n. The boundary condition that must be satisfied is the potential at that particular point this must be equal to 0. But the potential can be expressed in another way. This is also equal to minus q times n sub d divided by 2 times the permittivity epsilon sub n. Here we force x to be equal to 0. We force x to be equal to 0. So that's going to be 0 plus a sub n, forcing x to be equal to 0. And that's going to be equal to I'm looking at the wrong thing. We're forcing x to be equal to x sub n, not this 0. Everything was dropping out, and that should not be, at least not at this boundary. So we have x squared, so that will be x sub n squared, plus a sub p, a sub n, times x sub n plus b sub n. And consequently, b sub n is going to be equal to q times n sub d over 2 times the permittivity epsilon sub n times x sub n squared minus a sub n times x sub n. So consequently, we can now substitute b back into its original equation and come out with a modified form for our potential in the n region. And this is going to be equal to minus q times n sub d divided by 2 times the permittivity epsilon sub n times x squared minus x sub n squared. So we've got our signs are preserved, plus a sub n times the quantity x minus x sub n. So that is the new relationship for our potential. We only have one constant of integration to determine. Now let's look at the case where x is equal to x sub p, or I should say minus x sub p. For this boundary, we have the potential v sub p at x is equal to minus x sub p minus, and that's going to be equal to 0. So that's the boundary condition itself. But the potential v sub p can also be re-expressed in terms of the parameters of our problem. And this is going to be equal to q times n sub a, the number of acceptors per unit volume, divided by 2 times the permittivity epsilon sub p, times here x squared is now going to be replaced by minus x sub p squared, which is going to be x sub p squared, minus sign drops out, minus a sub p times x sub p. And the minus sign comes about because we're at the negative side of the x is equal to 0 axis, or point on the axis. And that's going to be plus b sub p. Okay, solving for b sub p, this is going to be equal to minus q times the number of acceptors divided by 2 times the permittivity epsilon sub p times x sub p squared plus a sub p times x sub p. Now let's substitute it back into the expression for the potential of the p material. And that's going to give us, here we go, function of x. This is going to be equal to the charge q times the number of acceptors per unit volume divided by 2 times the permittivity of our p material times the quantity x squared minus x sub p squared plus a sub p times the quantity x plus x sub p and that expression now is predetermined. Our last step is to satisfy the remaining two boundary conditions. Let's look at those boundary conditions. The first one is straightforward. The two are equivalent. So let us write it down. We will make use of these two expressions since we only have two unknowns left and two equations left instead of going back to the very beginning. Therefore, at x is equal to 0, the potential at in the P region at x is equal to 0 minus is equal to the potential in the N region at x is equal to 0 plus. Okay, so we set these two guys equal to 0, and wherever we see a factor of x, we make it equal to 0. So consequently, looking at this expression, forcing x to be equal to 0, this term goes away and that term goes away. So we have minus sign here, and a minus sign is positive. So this is going to give us the charge Q times the number, that was the N material. I believe that in order for our notes to be consistent, let's do the P material first. So again, we play the same game. Force x to be equal to 0. And hence this is going to be the charge Q times the number of acceptors per unit volume divided by 2 times the permittivity of that material times a minus x sub p squared plus forcing x to be 0, a sub p times x sub p. And now that's going to be equal to, for our N material, forcing x to be equal to 0, it's going to be minus, we have a minus here and a minus there, it's positive, this term goes away. So that's going to be Q times N sub D divided by 2 times the permittivity of the N material times x sub n squared minus a sub n minus a sub n times x sub n. Okay, so that represents one equation. The second condition, and we're going to do this a little bit in our heads, I believe. See if we can do that. The term that we're going to look at is the first term. We're going to take the derivative of the potential with respect to x, and then we're going to force x to be 0. So if we look at the first term, we take the derivative with respect to x, that gives rise to a factor of 2x. Forcing x to be equal to 0, that term goes away. We look at the second term, it's a constant, therefore the derivative with respect to x of a constant is going to be 0. The only term that survives is this term here, where we take the derivative with respect to x, and we get 1. The last term goes to 0 again because it's a constant. Hence, we can see that our next boundary condition we'll write that down here so you have it in a systematic manner. Okay, so again, we're going to take the derivative of our potential v sub n with respect to x, and then force x to be 0. So this gives rise to 2x, and x being equal to 0 goes away. That's a constant. That goes to 0. That's a constant, goes to 0. Derivative of x is equal to 1. So we are left with the permittivity epsilon sub n times a sub n. For the left-hand side of the equation. For the right-hand side of the equation, same thing. We observe that if we take the derivative of the potential v sub p with respect to x, the first term will give rise to 2x, forcing x to be 0, that goes away. This term is a constant, and this term is a constant, therefore its derivative goes away. And this term, the derivative of x is equal to 1, and that's going to give us the permittivity of our p material times the a sub p. So that's our second condition. We now have two equations and two unknowns, and hence we can solve for our solution. Well, I'm going to leave the algebra up to you on that. We do have to state another condition that's imposed in the problem. If you go back to the problem statement, and let's see if I can find that problem statement. Here it is. We are assuming charge neutrality. So consequently, satisfying this equation and this equation, subject to the condition that x sub p times n sub a is equal to x sub n times n sub d, this is what we get for the potential. So I'll leave this hanging around here. And this condition does give rise to a nice simplification, which is always looked for or welcomed. You should be able to demonstrate under those three equations, re-expressing the potential in the p region, function of x, will be equal to the charge q times the number of acceptors per unit volume divided by 2 times the permittivity of the P material times the quantity x squared minus, or x squared, no quantity, let's take this out. We don't need to go that far. So this will be equal to x squared plus x times x sub p. The potential in the N material, function of x, this is going to give rise to minus q times the number of donors per unit volume divided by 2 times the permittivity epsilon sub n times the quantity x squared minus x times x sub n. And we can determine the electric field directly, since the gradient of the potential is the negative of the gradient of the potential is related to the electric field. The electric field, due to the P material, and this is now a vector because the gradient operation is a vector, function of x, this is going to be equal to minus q times n sub a divided by 2 times the permittivity of the P material times the quantity 2 times x plus x sub p in the x direction. And this is valid for x greater than minus x sub p and less than 0. And finally, the electric field in the N material, this is identically equal to the charge q times the number of donors per unit volume divided by 2 times the permittivity of the N material times the quantity 2x minus x sub n in the x direction. And this is valid for x greater than 0 and less than x sub n. Now we want to show an observation. Let us go back to our geometry. Let's make it just a little bit bigger. Draw in our interface. And let us look at, if you look at these equations, x is between, look at this one here. X is between 0 and x sub n. So that implies that x is always positive. But if x is equal to 0, this term goes away, and we see the electric field's in the negative direction. If we force x to be equal to x sub n, 2 times x sub n is going to be greater than x sub n, and we see that our electric field is going to be pointing in the opposite direction, in the positive direction. Consequently, demarcating, I do have another colored pen here. See if we can give that one a little bit of a workout. Assuming I can find it. Ah, there it is. So let us look at the positions. This will be x sub n over 2. And this particular interface or position will be minus x sub p over 2. So when x is nearly equal to x sub n, our electric field is pointing in the positive direction. On the other hand, if x sub p is more towards 0, we observe that our electric field is pointing in the negative direction. Continuing onwards, if we force x to be equal to 0 in our expression for the p material, we see that our electric field is in the minus x direction. And finally, if x is equal to minus x sub p, this is going to be then negative, and that negative will be positive, and we see that our field is going to be in this direction. So consequently, we see that even though the ends of the contact points are grounded, we still have electric field just being distributed throughout the material. In particular, we know that our field line starts at a positive charge and originates from a positive charge and terminates in a negative charge. Our contact on the left-hand side is going to have positive surface charge. On the right-hand side, it's going to be terminated by negative charge. Okay, that concludes our discussion for today. And if you don't have any questions, then we'll see you on, what today is, Wednesday? So we'll see you on Friday.
Friday office hours? Yes?
Friday office hours.
Okay.
Okay.
Sounds good. I'll talk to you later, Dr. Schill.
You have a nice evening.
You as well.
Good night.